Hi, my name is Michael Podel, and I am presenting to you today my project on face recognition focusing on the principal component analysis method. Throughout the presentation, I will be covering the following topics: background of why I chose this project topic, the problem under study, current approaches using the principal component analysis method with an in-depth analysis of the techniques used, performance evaluation of the methods used, and a live GUI demonstration. Why face recognition? Well, I'm a double E student with an undergraduate at UCF and now an MSEE as an Edge student. I'm also a full-time Lockheed Martin employee and have been there for past 3 years. We are constantly working on projects involving military, defense, and security applications. These include detecting objects in the air as well as on the ground and water. Although this project focuses on face recognition, the math may be applied to other recognition objectives as well. In addition, this is a new challenge for myself. As an EE major, I am not as familiar with the programming algorithms in general. So due to my background with Lockheed Martin, I felt this would be a good stepping stone to exploring the abilities of the algorithms to detect faces and understanding principal component analysis. My goal is to be able to use this experiment as an advantage if and when I ever work on a program that is more vision-based. Problem under study. The overall objective of this experiment is to learn and execute techniques for facial recognition. There are numerous methods and evolutions of these methods used today. Some of the more common techniques include principal component analysis, linear discriminant analysis, and kernel principal component analysis. This study focuses solely on executing PCA, but the other methods are adaptable as well. PCA's main claim to fame is the ability to reduce the dimensionality of a dataset into a more manageable and more easily computable set of data. It is a statistical procedure that uses orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. This means that it is able to recognize the most useful data with the most energy and remove data which has little significance on the overall data and more importantly on the outcome of the algorithms. LDA is similar to PCA, but it uses the idea of dimensionality reduction with classes as seen in the figure below. LDA is able to characterize or separate two or more classes of objects or events. In addition, LDA explicitly attempts to model the difference between the classes of data. PCA, as mentioned before, does not take into account any differences in class, and factor analysis builds the feature combinations based on differences rather than similarities. KPCA is also similar to PCA, but uses kernel methods. Kernel methods are also designed to handle high dimensionality problems. It replaces feature vectors, which we will show later, with using similarities between other data points. The dataset used for this experiment is the AT&T database. This database is comprised of 40 individuals with 10 facial expressions each. The images are all in grayscale and have a resolution of 112 by 92 pixels, which is 10,304 data points per image. I felt that this database was a good starting representation of a set of people with different characteristics. This database allows me to vary the number of training images from 40 to 360 images. There are several databases that could easily be incorporated into this study if desired. The MATLAB code has been designed to easily be morphed into using additional data sets. This is a custom GUI that was designed for this project. I wanted to design something that was intuitive to use and would give the user, mainly myself, an easy way to explore the algorithms and results. The first input box allows me to vary the number of training images used per person. This value can range from 1 to 9 images. After this is entered, I will then click on the Load AT&T Faces button, which will load all of the training images into a single matrix described later. At this point, the first test image available is displayed in the test image figure. The input image control group allows me to move forward or backwards in the remaining images used for testing against the trained images. I can also let MATLAB choose a random image to easily try multiple people. The Find Person button will then execute the PCA algorithm and decide the best 5 matches. In addition, the mean face of the training images is presented to see what part the algorithm is looking at. Statistics are also generated, which shows the delta between the Euclidean distance of the best match to subsequent matches. This essentially shows that the confidence of the images, which is why the first image should be close to 1 or 100%. I also developed a macro which allows the algorithm to loop automatically through all the test images to determine the correct match percentage. This loop also cycles through the number of training images from 1 to 9 to generate how the algorithm improves or does not improve given different numbers of training images. The last button is a reset, which allows me to restart the GUI without closing and opening it back up. I have also placed a frame around each match, which will make it easy to see which images are matches and which are not. A green frame is a match, a red frame is not a match. These bullets list the PCA approach taken to execute the algorithm. So first we take the test images and training images and load those in. We then consolidate the training images, take the mean of the training images, remove the mean from each training image, generate a covariance matrix, calculate eigenvectors and eigenvalues, calculate eigenfaces, create phase space, find the minimum Euclidean distance, and then display the results. This is a blown up image of the GUI to show what the GUI looks like when it starts and the Load AT&T Faces button has been pressed. In this example, the number of training images is 3 per person. Therefore, the GUI returns in text format the number of images used for training and the number of images available for test. 3 images times 40 people gives us 120 training images and 280 images available to test with against the trained images. As mentioned before, the training images are 112 by 92 pixels for a total of 10,304 pixels each. Each image is then converted from its standard 2D matrix into a 1D column vector. Each image is then placed side by side in a new matrix. In this example, the matrix would have a dimension of 10,304 by 120. The average of the previous matrix is taken, but taken in a particular format. Because we want the average of all the images, the mean function is told to take the mean of each row in the matrix as compared to each column in the matrix. Irregardless of the number of training images, this resulting matrix will have dimensions of 10,304 by 1 or a single column vector. It may be difficult to tell from the 2 images on the slide, but there is a noticeable difference between the quality or smoothness of the mean face when using 1 image trained per person versus using 9 images trained per person. I will prove that the better this average face is, the better the end results will be. The next step in the algorithm is to center the training images, known as mean-centered images. The following images are an example of taking the original trained image, subtracting the mean face computed, and storing the output. This is repeated to each training image being used, in this case 120 images. Now that we have a single matrix of mean-centered images, we have to start determining the differences and similarities between the images. This process starts with computing the covariance matrix. A covariance matrix is used as opposed to just variance because the dataset is more than one dimension. The covariance matrix results contain vectors of scalar random variables. The covariance matrix from the previous step is utilized to compute the eigenvectors and eigenvalues. These are some of the main elements used to compute correct matches. Eigenvectors represent a direction in the set of data. The eigenvalues represent how much variance is found in the direction of the eigenvector. The eigenvalue is a number telling us how spread out the data is on the line or eigenvector. The largest eigenvalue found, i.e. the largest variance found, is considered the principal component. As a step to further reduce the dimensionality of data, a threshold may be applied to the eigenvalues to eliminate values which most likely contain little useful information and would not affect the outcome of who is a match. Eigenfaces is a term used when eigenvectors and eigenvalues are applied to face recognition algorithms. The eigenvectors were derived from the covariance matrix over a high-dimensional vector space of images. These eigenfaces form a basis set of all images used to construct the covariance matrix. This step is what will allow us to utilize dimension reduction. This matrix is computed by taking the matrix of the mean-centered images from before and multiplying it by the eigenvectors remaining after a threshold has been applied. We now enter the phase of the algorithm that will begin to finalize the data for comparison. Phase space is a projection of the centered images using eigenfaces from before. This is computed by taking the eigenfaces matrix and multiplying by each mean-centered image. These results are concatenated together into a single matrix. Let's assume that all 120 training images were retained. This matrix would be 120 by 120. This is orders of magnitude smaller than the original 10304 by 120 matrix. This new phase space will be used again shortly to determine the final Euclidean distances. At this point, the algorithm introduces the test image from the GUI. This image is also converted into a single column vector, and the average face is subtracted from it as well. This makes the test image also mean-centered. It is then similarly projected into phase space by multiplying it by the eigenfaces. This is the final calculation in the algorithm that will compare the training images to the test image. This distance is calculated by taking the test image in phase space and subtracting the individual training image also in phase space from it. Using this new vector of single values, the delta between images has been reduced into a single row vector with 120 elements at most. The minimum value in this vector is considered the best match. The next smallest value would be the second match, and so on. So now I'll go over some of the results. This is for one training image. So given that only one image per person was trained, there can only be one match. The top run shows that using the test image of this girl, the top 5 matches did not correctly identify the girl. As shown earlier, using one training image produces an unsmooth mean face, so expect the results to not be ideal. The bottom run shows that by using a slightly different test image of the same person, it did in fact correctly identify the girl as the best match. Here's where the plot of statistics is useful. Starting with the correct match on the bottom, the curve is smooth and holds its level of confidence until after only about 10 images, whereas the top curve is much less confident and is very jagged. In addition, it takes a steep drop-off at the beginning. Now here, we'll use 9 training images. So given that 9 training images per person was trained, it is possible for the top 5 matches to all be the correct person. The top run shows that using the test image, then the top 5 matches did not correctly identify the person. In fact, 4 of the 5 matches are the same incorrect individual. As shown earlier, using 9 training images produces a smooth mean face, so we expect the results to be much better. For the bottom run, I had to use a different person since only one image is left per person to test with. In this case, the top 5 matches were all correctly identified as the test image. Here the statistics are similar to before. Starting with the correct match on the bottom, the curve is smooth and holds its level of confidence until about after 40 images or so. The top curve again exhibits a sharp drop-off as its level of confidence takes an initial hit. After running the metrics macro from the GUI, the following data was returned showing the percentage of correct matches given a certain number of training images used per person. As initially expected, as the number of training images used increased, the best match percentage increases as well. In fact, there's a greater than 30% increase from the worst case to best case. This proves that the more images trained into the computer or processor of choice, the better the mean face quality is and the more accurate the mean-centered images are. This at the end will allow for greater accuracy in determining the best match. So in conclusion, the metrics run at the end do in fact prove that more training images does improve performance. The algorithms have been designed to reduce the dimensionality down to a single vector of face-based data. Using enough images will produce a high level of confidence for the end user. These matches could be backed up by using additional techniques in conjunction with this one for an even higher level of confidence. I will now switch over to the MATLAB GUI and provide a brief demonstration. Okay, so here is the MATLAB GUI that I demonstrated a little bit before. So we're going to start off with changing the number of training images used per person to 4 and click Load AT&T Faces. Again, it shows that 160 images are trained and 240 images are available for testing. We can then use the input image control dialogues to switch between images. So we can scroll forward to a couple people ahead, and then given this test image, we'll click on the Find Person button. This will then do all the algorithms and produce the results here. As mentioned before, the mean face is also calculated. In this case, the best match and the second and third match were all correct. As you can see from the statistics, there's a high degree of confidence up near 100%. I can now increase to the next person, click on Find in Person again, and let's see how it does this time. So now we got an additional fourth match, and again a high degree of confidence right at the beginning. So now we can reset the GUI, and we can give it 8 images per person, load AT&T faces, scroll ahead, and let's find person. Here we got all 5 matches, and again a very high level of confidence. Let's try one more image and select find person. So in this case we got 4 of the 5 correct. So this is a brief demonstration of the GUI. Thank you for listening to this presentation. I definitely without a doubt learned a substantial amount of information regarding PCA. These techniques and algorithms can definitely be applied to many fields of engineering, and I hope I can use them in my career in the future. Thank you very much.